Okay, so I'm going to talk about comparative planetary evolution, which is something that I think increasingly you're going to see happening as earth science departments, planetary departments, and departments of physics, math, and astronomy work together to try to understand the diversity of objects in our solar system and beyond. And so I like to think about evolution because it really adds in the historical component as well that has been so important for Earth. We increasingly are being able to extract this record from Mars, and I think we can go beyond that to exoplanets as we begin to understand their atmospheres. I like this particular view of what you can see here at Mars. This is Mount Sharp. It is a mountain that is 5 kilometers high in the middle of the crater that we chose to explore with the Curiosity rover. And one of the reasons we wanted to go here is because all those rocks that you're looking at are layered sedimentary rocks, but they are older than even the oldest rocks on Earth. They're about 4 billion years to about 3.8 billion years, except they're exceptionally well preserved. They're as well preserved as many of the youngest rocks that we would study on Earth. So we have a rare opportunity to maybe glimpse insight into the evolution of our own planet through studying the early evolution of Mars. Okay, so let me talk about exoplanets for a minute. This is a topic that receives a lot of attention, and as Frank mentioned, planetary science departments are now beginning to invade on the territory that is historically owned by astronomers, especially as we begin to understand their atmospheres. So for this particular planet, 186F, it is the first Earth-sized planet. There are many ways that you can do comparative planetology using sort of the diagrams that Robin was showing, where you can compare their diameter versus their orbital period and a bunch of other attributes. But what you're seeing here is a plot of this planet, which basically was the first one discovered in what's called the habitable zone of its star. And in this particular case, it's an M dwarf, so it's not as luminous as Earth, but it is within the zone where it would be illuminated with enough solar energy that water might be stable on the surface of that planet. This begets the question of what happens someday when we look at one of these Earth-like exoplanets, and instead of seeing carbon dioxide, carbon monoxide, and methane, what if we see oxygen? Where people jump to is this, and it is taken as a potential biosignature for that exoplanet. And so this then requires us to understand actually how Earth got its own oxygen envelope, which is a deeply historical problem that we can only understand through studying Earth's ancient record. And Mars offers another opportunity of a planet. We're motivated to send these rovers to Mars to ask the question, did life originate elsewhere? But to me, you can still make lemonade out of lemons if life never emerged on Mars, because it could provide the null hypothesis you're looking for to compare to Earth in terms of other models for oxygenation, which is what I'd like to talk about a little bit. Okay, so here's the record that we're familiar with that has built up over decades of understanding the history of Earth. We see evidence for a rise in oxygen at the end of what's called the Archean eon. And as we go into the Proterozoic time that you see here, we can compare it to things that we see in the geological record. So historically, people like Preston Cloud early on looked at rocks that are called banded iron formations, and that turns out to be something that's very important in the history of Earth. They're abundant early on, and then as you get younger, they seem to go away with rare exceptions. At the same time, people also noted a kind of a rock called red beds. These are sandstones. Think of the brownstones in New York City, Boston, or here in DC. Those are sandstones. They are bound together by minerals that are iron oxides, and all of the oxygen in those iron oxides is in the Fe3+ state. Turns out these rocks weren't present before what we now know to be the rise of oxygen. And then we also have paleosols. These are ancient soil horizons. If there's oxygen in the atmosphere, the iron gets weathered. It becomes insoluble because iron goes from the +2 state in the parent rock to the +3 state in the soil, and it is retained. But before that, it was stripped in the older part of the rock record here. And then we also have something relatively recent that has really been a clincher, some work that was done by Mark Tiemens and his student James Farquhar in understanding mass-independent sulfur isotope fractionation. When you look at the distribution of sulfur species on the early Earth, you see this mass-independent isotope fractionation effect that goes away once you've developed an oxygenated atmosphere. And that independently confirms these geological records, and until we can make that sophisticated measurement on Mars, and we are trying hard to do that, these other indirect records basically tell you the history of oxygen production on Earth. So we believe that right about at this time is when oxygenic photosynthesis was evolved as a metabolic pathway by microorganisms here on Earth, and after that it acquired its oxygen-rich envelope. Okay, so these are maybe some of the most famous examples on Earth. This is the Hammersley Iron Formation from Western Australia. These rocks are about 2.5 billion years old. Most of the world's iron derives from producing rocks like this, but basically the Earth rusted away as reduced iron was converted into oxidized iron, precipitated out, and became a deposit on the ocean floor. And this happened for a long time in Earth history until all that iron was basically titrated away from the ocean. We used to think that this was a signal of oxygenic photosynthesis, but my colleague at Caltech, Diane Newman, has done some influential work which shows that maybe anoxygenic photosynthesis could also do this oxidation reaction as well. Okay, so now what we need is to develop chronology. So basically Earth history is measured in two ways. One is that you have a relative time series, some property that you can keep track of in the rock record, and then if you can, you date that using the principle of radioactive decay. So generally our correlatable rock property that we're most familiar with on Earth are fossils. They appear, life evolves, they decline, they go away, new ones appear. And we can combine those with dating something like zircon, which gives us very accurate uranium-lead age determinations on those rocks, and so we can build a time scale. We can also, increasingly, for the part of the geologic record where fossils are not so abundant, we can use stable isotopes of carbon, sulfur, things like that, and also combine those with radiometric age dates to understand the passage of time in Earth history. Now on Mars, what we try to do is use minerals. And here you're seeing a reflectance spectra of sunlight that's being reflected off the surface, but with absorptions that correspond to the presence of H2O and OH in those minerals, and that tells us about the distribution of minerals through the history of Mars. We also did that early on in Earth. The term Cretaceous, which everybody's familiar with, derives from the Latin word creta, which means chalk. So early on, actually, geologists were mapping minerals as a way to bootstrap their way to the first history of understanding Earth's record. That was quickly eclipsed by fossils. So on Mars, we also look for other special things. There's a mineral called jarosite. It's a sulfate mineral, but it has potassium in its structure, which decays to argon. And we were actually able to make that measurement with the Curiosity rover. Ken Farley was able to actually do potassium-argon dating on the rocks on Mars and get the very old ages that were predicted by crater impact studies. Okay, so back to the Grand Canyon that Richard Alley was talking about before, and we do study these rocks to understand the environmental evolution of the Earth. We do this because we want to understand the tempo of biological evolution, and we want to understand that biological evolution is not just driven by genome development, but it is forced by the environment, which is, of course, what stimulates natural selection. So those of us that are interested in the history of the Earth study its environments to better understand the process of biological evolution. But there are also environmental records preserved in here which are independent of biological evolution and may represent the development of the planet. And of course, the most famous of these, here are these Permian red beds. And when at some point in the development of Gondwana land, the interior of North America got exceptionally dry, exceptionally hot, and a lot of these red beds were deposited at that time. But those are the things that are absent early on in Earth history. So we can go ahead and do exactly the same thing on Mars now, which was the goal of choosing this landing site. We had several to choose from, but the overwhelming favorite for the team was to go to explore this mountain called Mount Sharp, because what we saw from orbit down at the bottom of the mountain were layered rocks exactly of the type that we see in the Grand Canyon, except these rocks are probably 3.8 billion years old. And all the layers that you see here represent the chronology of the planet, the environmental evolution of the planet. It's like reading the chapters in a book. And if we start down at the bottom, we get the older part of the story, and if we go drive the rover up through these layers, we get younger and younger story. And right about here, you don't have to be a geologist to tell that something changes. These rocks up here are all different. From orbit, they have no reflectance spectra that indicates the presence of water, and we consider this to be the most profound boundary in the history of Mars. We call it the Great Desiccation Event. So when Earth, life was prospering and going on to evolve oxygenic photosynthesis, Mars apparently was dying, and in fact it was drying out. That's what we think this event records, and someday we intend to get up there. Okay, so if you go back to the Grand Canyon, the first scientist to really explore it and document what was going on there was John Wesley Powell, and this is his wheeled vehicle. You can see where the major sat. This is the original captain's chair. I'm not sure I'd want to go through the rapids in that, but he did. And they took thermometers and chronometers and notebooks and pencils and cameras and tried to do the best job they could. So now this is what we've got on Mars. The Curiosity rover for $2.5 billion of your money. This is what you get. Six-wheel drive vehicle. She's been operating on the surface of Mars for 2 years at this point. And just very quickly to go over the science payload, the vehicle has 17 cameras, including the one that took this selfie, where you take 57 frames, put it all together, move 3 degrees away, take 3 more pictures and Photoshop it in, and the public gets confused and think there's humans on Mars taking this picture. But we have fun doing that. And basically, in addition to that, there's a laser-induced breakdown spectrometer that can zap the rocks, and then we look at the emission spectrum in that case, which gives us a semi-quantitative understanding of what's there. The arm that you can't see can reach out in front. It's got an alpha particle X-ray spectrometer, as well as the hand lens imager camera that took this picture that you can see here. And in addition to that, we have a full weather station that I won't talk much about, but I will say that inside the rover, and the reason the Curiosity was so massive, she does weigh a ton on Earth. Inside there are 2 instruments, a quadrupole mass spectrometer, hooked up also a tunable laser spectrometer, and a 6-column gas chromatograph that allows us to understand these rocks. And then we've also got a toaster-size X-ray diffraction unit, so we can do X-ray crystallography. Okay. So a little bit about the environmental history of Mars. It's a good thing you're far enough away you can't read anything. Don't try to read, just look at the colors. These are rock successions of the type that you would see in the Grand Canyon. These are different locations around the planet. Here's what we get at Gale Crater, and you'll notice this is the most continuous section on the planet, and that's why we chose it. There are other locations distributed around the planet that we can go to, and if you organize things according to the relative age, the older areas are down at the bottom, and the younger areas are up at the top. We don't really have a good way to tell older from younger other than a relative sense, but everything that's green down here are rocks where they have phyllosilicate minerals in them, hydrated phyllosilicate clay minerals in them. And then those give way to hydrated sulfate minerals, which are the yellows. And then when you get up to the brown, that's when the planet dries out. And so wherever you go around the planet, you can see locations where there are rocks that are deposited that are beautifully layered, but they only contain anhydrous iron oxide, as best as we can tell from orbit. Basically, what these rocks document is what we believe is this terminal desiccation of the planet, which is, we think, this environmental catastrophe, probably due to the loss of a convecting core. When you lose the geodynamo, you lose the magnetosphere. When you lose the magnetosphere, you get solar winds stripping all the light elements, which I'm going to talk about in a minute. These are ideas that have been around for a long time that Curiosity is beginning to confirm, and in addition to that, developing some other ones as well. This is what we've got on Earth. Basically, 150 years ago, at about the time of the Powell mission, we have John Phillips, who was the nephew of William Smith, who made the first geological map. And by the way, this year we are celebrating the bicentennial of William Smith's map, which is the first geologic map ever made. And this is the time scale on Earth with 3 major subdivisions, of course, based on fossils, but this gives you a relative sense of our understanding on Mars. We're about 150 years behind where we are in understanding Earth right now. The difference is that advanced technology helps us leapfrog ahead a little bit. Okay, here's Gale Crater, and you can see Mount Sharp at the top here. I guess I'll have to purposefully use this pointer no matter what I talk about. This is the summit, 5 kilometers above the base where we landed. This blue ellipse is our landing ellipse. That's where Curiosity landed. And we are now over here and exploring the very basal part of Mount Sharp as we continue to walk up to the higher elevations. But we're not going to go much farther than here because this is where all the hydrated rocks are that we're the most interested in. Okay, actually, if I can just go back one, this ellipse is 20 kilometers in diameter, so the crater as a whole is about the size of the big island of Hawaii, just to give you a sense of scale there. Okay, here's our route. This is where we landed. We were supposed to be headed down this way, but our geological map told us to drive in the opposite direction. That took some discussion with NASA headquarters, but they bought it. And so the red indicates places where we drill. The green indicates places where, as we drive along, we use the laser to create emission spectra, and the yellow is where we stop and put out the arm to get the spectra from the alpha particle X-ray spectrometer. And then so finally we got down to here, we kept going, and then we finally crossed the boundary, and now in the last few months we've been working down in the lowest foothills of Mount Sharp in a different package of rocks that allows us to relate what's happening here to what we drove back across the plains. This is what we landed on. And again, you don't have to be a geologist to understand this. This is an ancient river gravel. And here's an example from Earth that's 10 million years old. Here's an example from Mars that's probably 3.8 billion years old. I can tell you this is the oldest river deposit you will ever see in the solar system. And so basically this was good because we wanted to pick a place where we would immediately encounter rocks that had formed in the presence of water. A lot of people said, NASA discovers water on Mars again for the 1,000th time. That's good. We wanted to pick a place, and we were very happy that we didn't get burned because that's what typically has happened in the past for a lot of Mars missions. So we landed, we found the evidence for flowing water, and we basically drove with the flow. We wanted to go downhill in this ancient river system to try to find the lake that was predicted to be at the end of it, which we found as well, and we drilled it. And here's what you get for your $2.5 billion, the pinnacle of human civilization, a drill hole about 1 inch wide. It's actually 1.8 centimeters wide, and it's about 7 deep. And here's what we did in the previous decade with the Opportunity rover. Didn't have a drill, and what you do is you have a rasp which grinds away at the surface, and what you see is when you do that, you make red powder. And the red powder is because of the presence of an iron oxide mineral called hematite. And again, hematite is what makes the brownstones in New York City and Boston red. And this is the Stockton Arcos, which is actually the material. You can see this at Princeton, just outside of the geology department. If you cross the street outside the geology department at Princeton, you get the gray rock, which was formed in the lake basin. And it's gray, not because it's full of organic matter, it's gray because all the iron oxide minerals are actually reduced. So what's interesting is that we see the red planet, and it looks red from far away because of the anhydrous iron oxide. 10 years ago, we're not so good at picking landing sites, and we picked one where we did see from orbit there was hematite, and we wanted to go there because the hematite does indicate interaction with water, and when we grind it away, we find out that the planet at depth is still red, which means it's oxidized. But 10 years later, we were thrilled when we drilled this hole, and we actually found gray Mars, and adjacent to the red Mars, which is the modern surface. So now we're getting somewhere in understanding planetary evolution. So here's what happens. I don't have time to go into how our XRD unit works, but this is the result summarized in some of the major phases that you see here. The column on the left shows the major rock-forming igneous minerals. If you go to Hawaii, this is the stuff that makes up the rock called basalt that you would see in Hawaii. We sampled it first by scooping up sand that was laying around on the surface by the rover to sort of give us a background sample of what we thought might be modern Mars not altered in water. And so you can see the abundances of those minerals here. And then here's the rock that we drilled that produced all the gray powder. And what you can see is that relative to unaltered Mars, ancient Mars, all these abundances go down, especially this one in particular, olivine, drops way down, and that's an iron magnesium silicate mineral. And what you see present that wasn't at all in modern unaltered Mars is 20 to 30% by weight, a clay mineral that's made out of iron, magnesium, and silicon, just like the olivine was. So it turns out what's happening is this rock is sitting in this lake, bathing in water, it's getting altered, and it's undergoing isochemical alteration. All the elements are conserved, they're just moving into different minerals. And by flying the XRD, we actually were able to prove that. The other thing that goes up that's quite important is the amount of magnetite. Not so abundant in the primary igneous mineral, but quite abundant in the alteration mineral that you see here. That's an important part of the story because we didn't find any hematite, which is iron oxide with all the iron in Fe3+ state. Now we find an iron oxide with some of the iron in the +2 state as well as the +3 state, so not quite as oxidized. Here's some more data. This is what comes out of our instrument that is hooked up to the quadrupole mass spectrometer. What signal intensity is over here. So we take the rock powder, put it in an oven. We can heat it up to about 900 degrees centigrade, and we capture the volatiles that come off as we heat it up. So one of the ones that we're most interested in is water, and water comes off abundantly in the beginning. It then declines, but then when you get up to about 700 degrees centigrade, there's a second peak here, and I'll talk more about that later, but that's the water that is structurally bound into these clay minerals. That's the water that we think is 3.8 billion years old. So now we can measure, if we could find modern water on Mars, we could measure its isotope ratio, and we can also measure the ancient as well. We can measure the D to H ratio in the atmosphere. The other things that you see coming off here are also important. Carbon dioxide is important for us because we are looking for organic compounds, and we think some of that is due to organic compounds, but a lot of it we realized was actually due to contamination. Oxygen is important because it turns out that there are oxidants in the rock that we drilled, including things that we think are responsible for oxidizing of the iron. And then we have two species of sulfur that come off as well. This one over here, you've got sulfide and sulfate. So we see sulfur present in the reduced as well as the oxidized state. Okay, so a little bit about that water that's then trapped into this clay mineral that comes off at 700 degrees centigrade. These are the hydroxyl groups that are bound into the clay mineral structure. And what happens is that if you measure their composition, they wind up intermediate between what you see as the reservoir on Earth and what you see if you measure the modern atmosphere today. And this is a measurement that was made by Viking. It was made by telescopes from Earth. It's made by orbiters, and it is also made by us inhaling the air directly adjacent to the rover. And what you can see is that it is intermediate in its D to H ratio between Earth and Mars, which is consistent with Mars losing its atmosphere by stripping of the light elements. And it also suggests, and there was a paper published by Robin Wordsworth at Harvard, that maybe we need to be careful about the discovery of oxygen in an extrasolar planet environment, because there are abiotic ways to do it, and this would be one of them. Basically, by stripping of hydrogen and photolysis of water molecules in the atmosphere, you could strip the hydrogen, enrich the atmosphere with oxygen, and get a false positive that way. So this is a couple of things to us. It is an indication that that process probably did work on ancient Mars, but it also means that there's a lot more water around Mars than what we once thought. And so I wanted to talk about how we sum this all up in terms of a simple cartoon about what we think we see at Gale Crater. It's hard for us to avoid a conception like this of relatively dry planet, but there's enough water around that there could have been snow in the mountains adjacent to the crater rim, and it might have also been atmospheric precipitation in the form of rain at times. It can flow down, and at times that crater filled up with water. And then it went away again. And as you eroded the rocks, they deposited these alluvial fans. So this cartoon down here indicates the bowl is a crater. The yellow are the rocks, is sediment being derived by erosion of the crater that represents alluvial fan. And the brown are times when the climate might have been favorable for water to have been stable in the crater. And then it fills up. And then what happens is, since that time, it erodes away, which is how we get the mountain in the middle. But these rock records are beginning to tell us about the oxidation of the planet. So I wanted to finish up by showing one last sort of detailed set of observations that we made. We took a path one time that led us into a valley, and when we explored the walls of this valley, we did our first detailed analysis that was downhill from where the rover landed on those river gravels, and we found something that we really did think was a lake bed. Here's the geology that you see. These look like the kind of rhythmites that you see in glacial lakes that once formed on Earth, whether it's the Pleistocene of the Connecticut River Valley or the Huronian 2 billion years ago in northern Canada. Centimeter scale, varve-like sediments, but here's the difference. These varve-like sediments, when you get down to the fine grain sizes, what you see plotted here is weight percent iron oxide. So we're up to 20%, 25% iron oxide down here versus grain size. So this is the coarsest stuff. These are gravels, these are sands, these are silts, and these are the muds that you see here. And what's happening is we see this fining in grain sizes, especially this bin over here, which is what we consider to be the diagenetic component of the rock. What we think is happening is that these rocks aren't just accumulating sediment, they may also be accumulating sedimentary iron formation. So this is quite a radical idea right now. Our team is 500 scientists, and not everybody's in agreement with this, but it's the direction that I think that I'm headed in, and one that allows us to begin to really compare what we're seeing between Earth and Mars. So finally, just to summarize, Gale Crater records a long-lived lake environment which lasted millions of years, we think, based on the thickness of the strata. About 3.8 billion years ago. The geological environment suggests it was wet. It may also have been warm. We don't see much evidence for glacial environments other than those varve-like sediments. So if warm is warm like the Pleistocene was, that's pretty warm compared to a lot of climate models for Mars. The hydrogen deuterium data suggests that there may have been 100 to 150 meters as a layer around Mars, which has been lost to space, that could have been present then. And I think the sedimentary geochemistry that we're seeing is beginning to suggest some comparisons between Earth and Mars in terms of the iron redox state. So thanks for listening.